have a couple people send me an email and say, "Hey, how do you do these couple of problems here?" And they were great questions. Story problems, oddly enough. Okay, story problems can be challenging. That's where we really want to put our thinking skills to the test there. And then we also had some questions on something that I didn't cover yet that I pointed out yesterday. So we left off right here on example number 8, isn't that right? Okay, so let's take a quick look at this. I don't remember exactly where we left off, but I think I pointed out this right here, and we said that has a name. What type of function is that? Piecewise, okay? Hope, why do we call it a piecewise function? It's in different pieces. How many pieces do we have here? We've got 2 different pieces. Now, how do I tell when I use this top piece versus when I use this bottom piece? Somebody tell us that. How do I tell when I use the top piece versus when I use the bottom piece? Noah? Okay, based on the function to the right, or here's what we call this. Okay, this is the domain for this piece right here. And this right here is the domain for that piece right there. So it depends on what I'm plugging in for t. All right? Now, here they said c of t. Normally, we choose a name for the function that represents what it's after. So this probably has something to do with a word that starts with c, and it's probably based on some variable that starts with t. So c is a function of t. That means t is the independent variable. We're going to plug in t, and we're going to get out a c. So let's read the question. The money C in billions of dollars spent for direct mail advertising. Well, let's see. Why would they say C for direct mail advertising? Yeah, because that's how much it costs. Okay? So the cost of direct mail advertising followed a linear pattern from 1990 to 1992, shown in this figure over here. Okay? And then it says in 1993, the money spent took a jump until 1996. So it was kind of like this line right here and then like a steeper line right here. So they didn't want to stay with just one linear pattern. They broke it into 2 different pieces. So can you see why it might be valuable to use a piecewise function? Lines are easy to work with, but not one line may not work for the entire thing. Okay? And then it says these 2 patterns can be approximated by this function. The cost, based on whatever the time is. So if we plug in a 0, a 1, or a 2, we plug it into the top one. If we plug in a 3, a 4, a 5, or a 6, we plug it into the bottom one. Okay? And it says t equals 0 represents 1990. You know how we did that the other day? Okay? Kind of lop off the gigantic numbers. Who wants to plug in 1990 into a function? Okay? Not nearly as much fun. Okay? So it says, use this function to approximate the total amount spent for mail advertising between 1990 and 1996. So here's what you'd have to do. You'd have to figure out how much was spent in 1990, 91, 92, 93, and so forth. So if I wanted to figure out what the cost was in 1990, first of all, am I going to plug in a 1990? No, what am I going to plug in? I'm going to plug in a 0. Which one am I going to use? The top one or the bottom one? The top one. And we're going to plug in a 0. So if I plug in a 0, I get a 0 out of this, and I get 23.4. And that's in billions of dollars. $23.4 billion. Tons and tons of money. Okay? So let's come back down here, and we don't want to do every single one of these, but here's what they do. They figure out the amount for 1990, then 91, and 92. Then they're going to use the other function to figure out for 93, 94, 95, and 96. So let's figure out why it's this for 1993. What number am I going to plug into this function for 1993? Okay, I'm going to use the bottom one, but what number am I going to plug in? I'm going to plug in a 3, okay? Because 1993 was 3 years after 1990. So then I look at this and I say, well, 3 is in this bottom one. So I'm going to use this one right here. So this is going to be 19.85 plus 2.50 times 3. And if I do the math on that, I end up with $27.35 in billions. So $27.35 billion that year. Okay? And then it says total. So what would we have to do to get the total? Add all of those up. Add all 7 of those years up, okay? And that's the amount that was spent. $197 billion, okay? A fifth of $1 trillion. That is a ton of money, okay? All right. Now, let's take a look at this one right here. And I mentioned yesterday, what does this symbol mean if you see it in the book? It means you're going to see something like that in calculus. These things are not going to go away, and it looked like a bunch of you were planning on taking calculus. So let's run through and let's take a look at this example. Then we'll do some from the homework. So on this problem right here, it says f of x is this function right here. And then it says find this ugly expression right here. Okay, if you lock this away in your mind, you're going to be a little bit ahead when you get to calculus. That is called the difference quotient. Okay, and the difference quotient is basically a way of finding a rate of change. Or in other words, it's a way of finding a slope. Okay, so it looks very complicated, but it's not all that complicated. So here's what we want to do. If we want to find f of x plus h, let's take this rule right here. And if I put x plus h right here, what do I do everywhere where there's an x? I plug in an x plus h. And I mentioned this yesterday. Whenever you plug something in, what should you plug it in inside of? Parentheses. So we're going to do x plus h, quantity squared, then minus 4, plug it in, x plus h in parentheses, and then plus 7. Okay, that is this part right here. Then it says minus f of x. Well, what's f of x? That right there, the original function. And then all we have to do is do a little subtraction problem with the two of those things and put it over h. So you'll notice they took this, put it right here, minus, and notice that they did this in parentheses. Whenever we're subtracting something, you'd always want to put that in parentheses so we can distribute through correctly. Okay? And if people make a mistake, this is where they make it, right here. What do you get when you square x plus h as a quantity? It's a binomial. You get this. Okay? It's a perfect trinomial square. And if you have any trouble with that, I would encourage you to do this. Do x plus h times x plus h. There's x squared. There's xh. There's another xh, and there's an h squared. So that's why we have an x squared, an h squared, and we had two xh's, so that's why that's the middle term. The rest of this is not too terribly bad. They distribute through here, so that's a minus 4x and a minus 4h. That's a plus 7. What happened here when we subtracted? What happened from this line to this line? What happened, Logan? We distributed through a negative, so each one of those changes. Now take a look at what happens here. Okay, if we go through and we collect like terms, there's an x squared, there's a minus x squared. There's a 7, there's a minus 7. There's a minus 4x, there's a positive 4x. So I've got this term, and this term. I've got those three terms. Are any of those like terms? They're not. So that's why I just write those three terms down. And what did they do from this line to this line? Factored it out. We notice that every one of those terms has an h in it. So if we factor out the h, then I can cancel it. I can't cancel it here and here. Okay, you can't cancel a term. You can only cancel factors. And this is the answer. Now, what's weird about that for most people is, my gosh, we started off with a function. Normally when we plug something in, we get a number answer. Plug in a 2, get out a 7 or something like that. With an expression like this, we get an algebraic expression for an answer. Okay? And then notice this little guy right here. Why can h not equal 0? Raymond? Okay. Because in the original expression, there was an h in the denominator. So we could have looked at this at the very beginning, and I've said this several times. If we're on a test and you look at something like this and you have no clue what to do, but you say, you know what, I'm not sure what to do with this, but I know h can't equal 0, maybe you get a point for that. Okay, so we always want to be aware of what we're allowed to plug into a function, okay, or an expression. Any questions there? Okay, all right. On the next page, so if you flip there, it's a summary of some of the terms that we've talked about. So it talks about what a function is. Okay, we could use this wordy definition and this wordy explanation, or we could just say, we said each, what did we say? How did we, each x corresponds to exactly one y. Each x can correspond to exactly one y. The opposite is not true. Each y doesn't have to correspond to only one x. Okay, we'll deal with that another time. Okay, but that's one way that we can describe that. F is the name of the function, or G is the name of the function, or C is the name of the function. Y is the dependent variable because it depends on x. That's why we call x the independent variable. And f of x is the value of the function at x. Or in other words, f of x is exactly the same as y. Okay, it gives us the y value, or the function value. We talked about domain and range. How could you keep straight which is which? What is it? X is domain, y is range, and it's because they are alphabetical. Let's say we take a look at this one right here, just really quickly, just to kind of review some of the ideas. Take a look at that. Is that number one, is that a function? It is, because each x corresponds to one y. Okay, look at number two. The question is that a function? If it is, great. If it's not, can you explain why it's not a function? Can you tell us why it's not a function? So raise your hand if you can tell us what the answer is and why. What's the answer and why? Tara, what's the answer? It's not. And where's the problem? The problem is at -1, because that -1 is an x, it's in the domain, and it corresponds to 3, and it also corresponds to 4. Okay? We're going to talk about why that's a big issue when we start covering 1.4. Okay? Let's skip ahead here. Has anybody, well, I know several of you have started the homework. Any questions before those tough ones toward the ends? I'll just point out, I kind of like how they set this up, how they have this little placeholder. Okay, you'll hear me say that a whole bunch. If we want to find f of 4, we'll write the rule f, which in this case is 1 over something, and just put that big thing in parentheses. And then what are we going to put right here? We're going to put a 4. Okay? What if there was a bus right here? What would we put right here? We'd put a bus. Okay? What if there was some nasty algebraic expression right here? We'd repeat that nasty algebraic expression right there, and then we'd figure out what we need to do to simplify it. Okay? Any questions? Okay. I do want to take a look at, let's take a look at number 77 right here. Okay? What's that little symbol off to the side? Okay. That's a difference quotient, okay, or a type of difference quotient. So we're going to want to be familiar with that when we get to calculus. So let's take a look at this one right here, and let's go ahead and do this problem. And I'm going to grab a separate piece of paper. And we've got x squared minus x plus 1. And they want us to figure out f of 2 plus h minus f of 2 all over h, right? That's what they're after. And what else did they put with this expression right here? Okay, h can't equal 0. Okay, you can plug in anything for h except for 0. Okay? So let's figure out what f of 2 plus h is, because that's that first quantity right here. The rule f is something squared minus that same something plus 1. And what is that something that we're plugging in? 2 plus h. So let's figure that out. Take a good look at this. Please don't make that common mistake there. Go ahead and write down what we get when we square that. Let's see, Nathan, what do we get? Very good. Okay. Brandon, what do I get when I distribute through here? Just distribute the negative through. And then we get a +1, right? Okay. That stuff is this right here. F of 2 plus h is right there. Okay. Then I'm going to write minus f of 2. So let's figure out what f of 2 is. F of 2 is 2 squared minus 2 plus 1. What do I get? 4 minus 2 plus 1 would be 3. And then the denominator is just h. Okay. I think everybody can finish it from here. Are there any questions? Okay, so you're probably going to be in calculus 2 years from right now, and about 3 weeks ago, you would have been doing a whole bunch of this in a calculus class. Okay, so let me show you something interesting that happens here. I'm going to take these off. I'm just going to distribute through. Okay, and I want you to notice what happens here. Let's see. If I go through and I cancel, I've got, well, let's see, I really only have some numbers that are like terms, and then maybe some h's. So 4 and 1 make 5, and what do -3 and -2 make? -5. So I can cancel all those off. The numbers completely go away. And then what I've got is 4h minus h, so that's going to be a 3h, plus an h squared over h. And what do we notice about that? Yeah, you can factor that. We've got a common factor of h in each one of these, so this is going to be 3 plus h. That's all over h. And then I can cancel those off. So the answer on this one is 3 plus h. Hey. Any questions there? Okay. All right. We had another question on these guys right here. So we're going to take a look at, let's see, 92, and what was the other question? 94, okay? So 92 is kind of interesting. Let's take a good look at that one. And I think there's enough room right here that we can do this one. And then we'll look at 90, the other one. 94, did you say? Okay, all right. So these are both even problems, so they're not in the back of the book. That can be good and that can be bad. Okay, this says a rectangle bounded by the x-axis and the semicircle. So here's the function for the semicircle. And it says, see the figure. So they've drawn a picture for us. And in a story problem, drawing a picture is a pretty darn good thing to do. Okay, especially with a geometric example like this. And it says, write the area of the rectangle as a function of x and determine the domain of the function. Okay, so let's take a look at this. See this point right here? That point right there is xy. I realize it looks like it might be 5, 3.2 or something like that, but it's not. It's just xy. So I'm going to draw this rectangle over here. And my question for you is, if this point right here is xy, can you tell me how tall it is? Don't say anything out loud. If that point right there is xy, can you tell me how tall the rectangle is? Raise your hand if you can tell me how tall the rectangle is. Okay, got 6 people, 7, 8. Sarah, how tall is the rectangle? It would be y tall. Okay. Now the next question is, I'm going to break this into 2 parts. The next question is, how wide is the rectangle? So if this point is xy, the question is, how wide is that rectangle when we're going to break it up like this? Okay? Some people already know. How many of you know exactly what the width of that rectangle is right now? Okay? For those that don't, we're going to ask this. I'm going to say, how far is it from here to here? If this point is xy, how far is it from here to here? And once you figure that out, how far would it be from one end of the rectangle to the other end of the rectangle? I think Cameron had his hand up first. Cameron, how far is it from here to here, the whole width? It's 2x. Because from here to here would be x, and that would be x. Okay? Now, I'm going to erase, okay? I realize you can probably still see that, okay? Let's cover all that stuff up that's highlighted. Stare at that rectangle for just a second. You've all had some geometry. Area of a rectangle is a formula you really shouldn't forget, along with a triangle and a circle. Who can tell us the formula for the area of a rectangle? Looks like Logan had his hand up first. Logan, what is it? Okay, width times height, or base times height. So we could say base times height, length times width. There are a bunch of different ways to talk about it, okay? So if it's base times height or length times width, what's the area of this rectangle? The base is 2x, and the height is y. You with me there? Okay, now keep ignoring all the stuff that's blocked out there, that's highlighted. That's the answer. Is that hard? Look at the diagram, the rectangle, figure out how tall the rectangle is, figure out how wide the rectangle is, and then come up with a little equation that represents the area of that rectangle. You with me? Okay, now let's come back and put this in context. And I mentioned this yesterday. What's wrong with this if we're talking about the area as a function of x? What don't we like about this? Noah's got it. Tammy, what is it? What's wrong with this? There's two different variables over here. We wanted the area as a function of x. Here's what we're really after. We're after a of x, and then what comes over here should only have x's in it, right? There's nothing wrong with what we've done here. It's just that it's got this extra variable y floating around. So, is the 2 okay? Is the x okay? The y is not. Stare at that problem for just a second and see if you can figure out how we can get rid of the y. Peyton? Yeah. Okay. This is basic substitution. It's kind of an ugly substitution, but it's basic substitution. The way I always explain substitution, if somebody comes to you and says, hey, can I have $1? And you hand them 4 quarters, is that what they were asking for? Kind of. They probably wanted a dollar bill, though, didn't they? You gave them 4 quarters. It's the same thing, it just looks different. So in our little equation here, we said there was a y. It was asking for a y, but if I put the square root of 36 minus x squared in its place, I gave it the same thing, it just looks different, right? And what's the advantage of this expression right here? It's all x's. It's all in terms of x's, okay? So that's the answer right there. Then it says figure out what the domain is. So let's stop and think about this. If we're going to make rectangles underneath this semicircle, I could make rectangles that look like this. Everybody watching? I could go over a little bit and up and over and back like that. I could make a rectangle like that, in which case x would be a really small number, right? Or I could make one that goes like this. Way over here, barely go up at all, and then over for that top part of the rectangle. Okay? So what is the smallest x could be? Okay. We could make it -6, but here's the problem. What if I used a negative here? This would be a negative times a positive. What's a negative times a positive? Negative. Can we get a negative area? Nope. So we better not use negatives. Okay? So what would be the smallest value for x that I could possibly use? 0. Okay? So the domain is going to be 0. And what's the largest value for x that I'm going to use? 6. Okay? Now, square or round? Logan says square. Anybody want to say round? Can one of them be round? Hey, Logan, do you think they both ought to be square? Okay. Tell us why you think both of them ought to be square. Okay. So if we plugged in a 6, we get 0 here, which is okay. We can multiply by 0, and we can take the square root of 0. Okay. If we plug in a 0, I get 0 here and 36 here, which when I multiply everything together, I still get 0, which is still okay. What does that mean about the rectangle, Logan? What type of rectangle do we have if x is 6? We have a rectangle. So does it have any area? No? Does that work? Okay. So anyone want to argue for having round brackets? I'd take either. Okay. I think they're both fine. Now, in the real world, if it said you had to have a rectangle, there had to be a rectangle here, would we have square brackets? No. You'd have to have round brackets. Okay. If x is 0 or if x is 6, you've gone straight up and straight down if it's 0. You've gone straight over and straight back if it's 6. So you don't really have a rectangle. Okay. So you'd have to do open endpoints there. Any questions there? Okay. Take a look at the next page, and the next page has an excellent problem. It's this one right here, number 94. This is actually true. Okay? The Postal Service has these type of regulations. It says a rectangular package to be sent by the U.S. Postal Service can have a maximum combined length and girth. Girth, what does it say girth is? Yeah, it's like the perimeter around the widest part. Okay, it's like the waist of the package. Okay, it has a total of 108 inches. It says the volume of the package as a function of x. Okay, now we're going to do the same thing we did just a second ago. We're going to ignore everything on here, and I'm going to write v equals. Everybody here should know how to find the volume of a box. Logan, what is it? What's that? Okay. Logan doesn't know. Anybody else want to admit they don't know? Okay. We got a couple people that do know and a couple people that don't know. Okay. Volume of a box. Area of the base. So it's the length times the width. And then times it by one more thing. Hop. The height. Length times width times height. So the volume is length times width times height. Okay. Stare at this picture for just a second and tell me what V is. Length times width times height. Sven, what is it? Y times x, so y times x squared, right? That would be the answer if they didn't say the volume as a function of x. So again, I'll ask you, what don't we like about this? We don't like the two variables. We've got to get rid of one of them. We've got to get rid of one of them. Okay? And what we're after here is, if you take the length and add it to the girth, by the way, if this is x and that's x, what's this over here? And this right here? So if I add y plus x plus x plus x plus x, in this particular problem, for this postal regulation, if they're going to take our package, what's the largest those can add up to be? 108. Okay? And that right there should be enough to finish this off. Okay? So I want you to spend some time thinking about it. This type of problem will not go away. In fact, I can almost guarantee you'll see a problem like this when you take Math 1050, and I guarantee you'll see one like this when you take calculus. This would be a classic calculus problem that you can solve using calculus, and in pre-calculus you can solve it using a calculator. Okay? Any questions? Sure? Okay. That reminds me, if you would, let's see. Starting tomorrow, if you'd make sure you bring a graphing calculator, okay, I'd appreciate it. We're going to be doing a calculator skills worksheet, and you need a graphing calculator. If you don't have a graphing calculator, you can check one out in the office. Most everybody paid a $10 rental fee, so you can check one out there, okay?